As our next speaker is Artur. He's the systems engineer at the Energy Logserver, and he's going to talk about how do we enhance the security operation capabilities by employing also artificial intelligence and developments in machine learning.
That's right.
Well, there you go. Let's start.
Thank you very much. I'm very excited taking the stage after Marvin and having you here because we continue the same subject, and I hope what I will show you will be a little bit different, so you can compare, pick the one approach you like. Also, we can discuss what can be done in a different way. So I'll be speaking about the role of artificial intelligence, how can we put that together with security analysis. My name is Artur Bicki. I'm working in Energy Logserver as an architect. We focus on log scale, log analysis, and in fact, we jump from the same base as Elastic. We have Sciene underneath, so the technology you will somehow recognize. Today, I want to focus on some bullets, what kind of challenges we do have while building security operating center. So the biggest problem is the amount of data that we need to analyze on a regular basis. In my projects, how we deploy the system, it's just a regular problem that we need to tackle a terabyte of human-readable text generated a day. That ends up with a level of 200K events per second. So it's obvious that this human-readable text cannot be read. So in SOC, we need to hire our experts, and if we added 24-hour service, we end up with high costs. So the real need for enhancing that is to tackle those 4 problems. So our AI need to work in a large scale, to be fast. It cannot rely on signatures, because the dynamic world of attackers is changing rapidly. So the detection rules, the engine, need to adapt to any new scenario that comes every day. On the other hand, we cannot expect our SOC guys to have expert knowledge in AI, because AI need to be a regular tool, like one of the ways to analyze our threats. No one would be having diploma in math, but still algorithms can be complex. What we propose is a little bit different approach that you've seen from Marvin, because we try to share scenarios into different use cases. That is because of math, in fact, because math and algorithms that we use very precisely analyze logs that we put there. So, in fact, text, words are totally different from numbers, which is obvious. So you cannot use AI as a black box to detect just out of the box that you should expect some results without driving algorithms to correct approach. So let's see how we can deal with those different logs. First example is a text, finding anomalies in text. And here we start, of course, with reading subset of logs, and what we do differently, we want to calculate statistics for every word that appears in this data set. So having the logs parsed, we want to find out how often each word appears in the data set. Once the statistic is calculated, then we can recognize common words, things that are seen very often and they are known. We can get rid of it and concentrate and focus only on rare words. We introduce something like rare word, Once the log contains many rare words, we score it, we show it to SOC guys to analyze. Not sure it is clearly readable, but the numbers I want to show here is a simple HTTP log from 7 days from our lab. The number here is important. You know that it can be a big amount of information, more than 1 million records. Some examples here. It's difficult to spot anything special. But if we run statistics after parsing the statements, we see that words like HTTP, our browser type, file system type, operating system type, appears very often. Of our interest is, of course, the table on the right-hand side that contains unique words, things that happen very rarely. Could be random generated domains that our colleague told us about, random APIs, maybe it's a script that someone injected to our web server. The number of occurrences tells us that this is something special, and we should focus on logs that contain that rare words. Similar table that we have from mail server, typical on this side, user from session we will see very often, but that random users, random logins should be checked immediately. Windows has own way of presenting data in events. But if we calculate statistics, we can recognize dynamic packages that are being initiated on the machine, maybe dynamic registry keys. Everything that is suspicious, we will see as rare words. How could that work in production? We took HTTP logs, and we also run geolocation algorithms to have country names taken from the IPs. If we analyze what is rare there, immediately we can recognize connections that are uncommon. Saudi Arabia, Kazakhstan. Maybe we should look closer into this. Same source, but even we had a question from the audience last time, how to detect things that contain attack. This is SQL injection. We have here select, union, somewhere there, and this binary string, which for sure appeared only once in our 100,000 of messages. For this approach, it's extremely easy to detect that kind of strings. We show what is rare for us. We give it a score. We put it on the special graph. We call it spread of anomalies, because each entry will be summarized with anomaly score. That's why here, as a dot, is the highest anomaly. Usually you will see a picture like that there are some key players on the right-hand side, and the rest of the anomalies grouped together on the left side. Dictionary attack is also a perfect scenario for that approach. If the attacker is dynamically hitting our username and password, he always run out of time, so very quickly we will see that the pattern changes. When we build the dictionary, we see the statistics. Very easily we can detect random usernames and generate it as an alert for SOC. Also, that approach can be used to simply have a perfect infrastructure, not only scanning for threats, but looking for different errors, like in that example coming from VPN gateway. The rare pattern was the ID of an error, but when we looked in the internet what is the description of it, we can pass that information to our network guy to fix it, not to overflood our SIEM. what we are suggesting is that every source comes from the vendor, and the log message is using predefined set of words that we can analyze and create something called vendor language model, kind of dictionary. Somehow, administrator recognizes logs. He knows that they are coming from a mail server or a DHCP or whatever. He knows the expert knowledge because he understands the logs. We try to do the same. We create vendor dictionary, we save it, and then very easily we can detect any uncommon vocabulary that comes from the source, because it never happened. Like in that example, when we stick to this method to analyze firewall logs, we have some key player here, and its score. There was a problem with one of its firewall rules. We can take one step forward. Now data are segregated into the normal ones and the logs containing attacks, because we already statistically could recognize them. Now we can use language model to additionally train. In that example, we use BERT from Google, which comes pre-trained, but additionally we can add our own knowledge to let the model decide whether the log is of normal behavior or not. Because we do contain the knowledge, we already classified that on entry. Training is very simple. There is a little procedure for that. Sample example of SQL injection that can be used to retrain the model. What is the end result is that language model can understand semantic of everything that was taught. And the further detections rely on similarities between vocabulary and the context, not exact pattern recognition. So in first step, we try to catch uncommon behavior of words in our logs, and then we use it for training and understand how the log is built. We want to create that kind of models for every kind of attack. At first, we will analyze, we will divide our logs into the ones containing SQL injection attack, dictionary attack, cross-site scripting, and we'll use that to build different models for different sources. Once done, that can be put upfront and work in real time to have immediate recognition of what is suspicious without any background task. Right? Numbers are different. That's why when we talk about numbers, we need to pick up different algorithms. Of course, we read logs, but we need to concentrate on fields that contain numbers. We learn what was the behavior of single number or values connected with each other. And we can detect changes. The algorithms used here is a very simple isolation for us. It works like that we partition the data. And if we can isolate a sample with a simple one partition, it's an anomaly, it's an outliner. But if we would like to isolate that dot here from our samples, you see that we need to divide data in many times, which means that the dot belongs to a group. So we want to find those outliners, analyzing numbers. OK, but in fact, using logs is not easy to find numbers, because we have still human-readable text. This screen comes from user behavior analytics component in the system. it is a part in the platform where we can count each action performed by a user. How often has he logged in? What has he touched a file, a folder, installed a package? We count each action to create something like a profile. Once having numbers that describe the user, we can use it for training the model, in fact, on numbers. That is a real behavior of a user, and in that moment, we see that the attempt was made to access an object, high number, and the model detected this as a rapid change in the behavior. That's why we can put together regular behavior with those spikes that shows us a moment of anomaly. Okay, what can we do if we do not have numbers at all in logs? We can count logs always. It's a good number. We need to focus on the time window, and then we measure how many logs we have in 50 minutes, in 1 hour, and that will be a good number to build a model. This approach can be used to detect DDoS attack when we have significant amplification in logs. There is a log count peak easily detected by algorithm. Each time we mark data in our database, so that later you can integrate with external system, with SOAR, send it to further analysis. Very different approach is forecast. Because forecast, we are using the algorithm XGBoost to really produce forecast, to generate a forecast to the future. We can use it to track application behavior. How many sessions do we have? What is the typical response time? We can build a model and generate samples to the future to actually see them. We can predict disk space utilization and forecast when that will finish. In the system, you will find a dedicated alert that can compare data that we forecast with the one that are coming in the real time. Screen is pretty obvious. With the yellow color, we've got the history, shape, historical signal, and the model try to predict its behavior. They are all values, they are all numbers. Clustering. Something very, very different, because in the examples before, we need to think whether it's text or numbers, and with clustering, we don't. Cluster is a method of grouping. We can take the whole message and see whether one log resembles other. We try to find like islands of similarities between logs. What we are looking for is, in fact, a distance between each log. How could that be? After reading, we convert log to number vector. It's not that easy. But if we have vectorized our information, we can measure dimension. If the dimension is large, it's far away from each other, then it does not create a group. But if the logs are somehow close to each other, numbers are close to each other, the entire information most likely will be having the same format. I'm pretty sure it's the first time you can see logs. You can graph them. So the algorithm is creating that visualization that is coming from your logs. We can see examples. Not everything is on the graph. It will be too many. But we see what is the regular shape, whether we see, how many groups we see? 4, 2, 1? It depends on the, we need now the expert to tell us what's inside each group. Because in that example, with HTTP log, the algorithms put together entries from prop find method. Another collection was post methods, different post method, but containing different URLs. So the algorithm discovered that it's not similar to the one before. And the last one is most important because without any additional knowledge, the algorithm put together all the errors. It is unsupervised. We haven't pushed any information up front. He just turned it to numbers, put it on the graph, and see, hey, this is the group that does not belong to anything else. And no surprise, because it's errors. It must be different. Again, we use a tag that you know from schema. We can enrich information, original information with the tag, and focus attention of SOC guys to look only for that group. We can create alert just for that cluster, how many messages jumped there in 15 minutes. Because we are not interested in all the others. The same algorithm can do categorization. We see here sample of Linux log, message log, and the cluster was created from inode information. But the same log contained entries from SSH. But the obvious difference you can see on screen, they look different, and that's why algorithm created those two islands. Why is it important? Because with large deployments, we have thousands of sources, and it's very difficult to categorize them up front. If we build a model for clustering that is capable of dividing information based on the importance or any other criteria, we can store it and use it in real time to filter unnecessary data for our SOC team. This example comes from logs, HTTP logs that contain application code, like 200, 400, 500, and that's why all the rest is the same. Only difference was the status code. That's why on the example we could see 4 groups. The root cause. We put together a root cause with a knowledge graph. Root cause is a very hard topic, let's say, because it's easy to talk about root cause, but in fact, no one will tell us exactly what is the exact root cause. And we don't want to change this. You need your knowledge to be 100% sure what is the root of your problem. But when we are looking for a cause, first, we want to build knowledge from our data. Why? When we have deployment for hundreds of sources, thousands of sources, it's obvious that not every talks to each other. There are things that are working together, but we have different divisions, different departments, and there are systems that never talk to each other. So we have an algorithm that will try to see whether systems are somehow dependent on each other. We calculate coefficient from Pearson correlation. So we look for a number. A good example is a pink result. If we put here kind of number that can be compared between systems, we can see that if we have a network breakdown, this number affects a lot of sources. If we analyze the whole history, we are able to calculate this coefficient and see what systems are correlated, because that pink request changes in the same moment. This coefficient starts from 0 to 1, but we want to filter out everything below 0.7. So our knowledge will contain information about the sources highly correlated because of having the same reaction to ping in the same moment of time. Okay? Result of it is a graph where in nodes we have sources, and the numbers here are telling us how many other systems are correlated. In fact, this is very crucial information because it's also importance of that source. If it's correlated with many others, with 9 other systems, it is important. You can use it for your CMDB to see that things are working together. This graph is created automatically. We have an option to change the correlation coefficient, to see what is highly correlated and what not. So now we see systems that have something in common. We can save it, and during logs discovery, we will use that saved model to filter out again sources that are not working together. They had never chance to react in the same way. So this same component of discovery tab. We have a new tab here, a root cause, where you can look for your one of the entries. You select a model to check whether our source is connected with others. So in fact, we are filtering all the results out. We don't want to analyze sources from different cities. The missing point for root cause is time. We filter out all the data, and now we are just looking for the starting point. When did it? What was the beginning? That's why the root cause analysis needs time perspective. Our goal is to end up with a single entry that comes from the connection with the knowledge graph and the time. We have some minutes left. I can jump to the system. Maybe you have a question in between. Please ask if you'd like to.
Sure. While the live demo is being prepared, if there are any questions, just raise your hand. There is one question. Oh, wait for the microphone, please.
Can I get the screen back?
Thanks. A quick question. When you plotted the logs, there were 2 clusters, each of respective color. Then there was one occurrence of the same color at the axis in 0, which is possibly to expect. And there was one more third color, just one green dot, not far away from the axis. Interesting. How come it got there?
Yeah, I have a chance actually to check it. You saw it correctly. Yeah, it need to be verified. I think there is some technical issue when I presented the presentation, and they had to be more clusters, in fact.
Thanks.
Okay. So, as I said, the AI part is a component of a typical of dashboard of the menu here in the system. And what we are actually doing is we introduce the algorithm to the data that are already in the database. So we work on the safe search that most of you probably know. So we have the searches for HTTP logs, for Windows events. There is no additional database. Everything is stored in one system. We only analyze that as a job. How does it look like in details? This is the one prepared for numbers analysis. We have a time perspective. We highlight each detection with score. And we put it on the graph of spread of anomalies. That dot is responsible for number of numbers coming from user behavior analysis. That's why once it's detected, we can put that together with real data using dashboard for user behavior. Where each detection is marked along with all other actions that user performed. If you would like to see how text analysis work, okay, let's jump from here. It's sorted from top anomaly. Oh, sorry. Okay. Let's look in details what is here. So we have original information, and below we see how many words are rare. What are the rare words here? We can check the others as well. Each detection is enriched with the information about scoring. So the original log is here. I can jump back to Discovery tab and see the result. We enrich the log with this schema. AI. You can find information about the rule itself, and the score and the rare words. Okay. And to check. I close that one. And the clustering, how in the practice it looks like, there is one piece of information that I haven't described. Creating the rule, we can suggest the algorithm what do we think, how many groups we expect. But the algorithm itself will try to guide us and create this, we call it an quality of each group. Because if we share that too much, if we divide a cluster into too many groups, we will lose information. And that graph is actually telling us, if we tell the algorithm to create 6 groups, the amount of information in each group will be small. It will be much better to keep 3 groups here, or 4. We can check that on the graph here, what is actually hidden under each dot, what kind of logs. And below, we have a name of the cluster that will be used for tagging and examples. They are just examples, of course, because behind that task, there were millions of records. That's why we have just 10 random examples that will help us identify the meaning of each group. If you are satisfied, you can save the model. Thank you very much.
Thank you. We do have time for a few questions. I will start from my side. I mean, clustering, in my experience, it's not an easy task. What kind of model or algorithm do you use? I'm pretty sure that you're not using k-means because you need to predefine already how many clusters are there. Most likely db-scan derivatives like db-scan. K-means. Mm-hmm. And every time when you generate clusters, you calculate the SULET score or any other score to identify if that is is appropriate. So that's why you have the quality graph.
Exactly. There is a, I haven't showed it, but in the, when you create the rule, there is a place where you can guide the algorithm from how many clusters to produce. But it can be adjusted right after, because when you run, the algorithm will tell you with the graph, are you mistaken or not? And then you rerun with the correct number if you are then satisfied. Once it's saved, you can take it up front to your listening part of the system, and then data are categorized in the real time with that performance, because it's very heavy to run any analysis with terabytes of logs daily. That's why it's very important to very quickly push that up front.
Is there any reason you would not want to use already the hierarchical clustering models like optics or HDB-scan, or you found that the best performance is for the k-means?
Yeah, that's the answer. We found that our own approach is best because we control it, we analyze. It was not just the algorithm taken. There was 1 year of work behind it before we were able to see actual results. In fact, the results I'm showing are after cooperation with Warsaw Polytechnics, where we have support from real mathematicians.
Well, I'm happy to see that you're using the statistical machine learning models that can be used offline and applied directly onto the data set. So absolutely, I see a direct difference from what the Elastic is doing and what yours approach. So that's very good. Are there any additional questions from the audience? If not, we have already reached 5 o'clock. That's the end of today. Let's give a round of applause to our speaker.
Thank you.